So now in this lesson, we want to discuss fluorescence. And we can imagine that fluorescence is the opposite process of an absorption event. And we previously described some binary system with a ground state and an excited state, in which we have some light energetic enough to bring an electron up from the ground state to the excited state. And now, with that same kind of binary two-state system, once we have our excited state electron, it's then going to radiatively recombine and emit another photon. Fluorescence, as we can imagine, is not going to happen on the same time scales as absorption. And we can imagine that this radiative recombination is a pathway that allows energy to be dissipated inside of the system. But let's look at it in the same way we would as a reaction. And let's have a fluorophore F absorbing a photon of h frequency, Planck's constant times frequency, thus producing an excited state fluorophore. And we would know this as absorption. And then our excited fluorophore can de-excite, going down to the ground state and emitting another photon. And of course, this is rendering our emitted photon during our fluorescence event. An easy way to visualize these processes of absorption and fluorescence is a Jablonski diagram. And a Jablonski diagram will show a combination of our electronic manifold with a certain number of vibrational quantum states, and we can call this E1, and then our excited manifold, which will also have a series of vibrational quantum states as well. And so when we have an absorption event and our electron is excited, our system is excited not only electronically but vibrationally, this absorption event should happen on the attosecond time scale, which is 10 to the minus 18 seconds. And then we can end up having vibrational relaxation if we go into a vibrationally excited state. Our vibrational relaxation is happening in the femto to picosecond time regime, which is 10 to the minus 15 to 10 to the minus 12 seconds. And the energy spacing between these vibrational modes is relatively small, and therefore, as long as there are many modes that allow for this de-excitation to occur, you will eventually get back down to the most vibrationally relaxed state at the edge of this lowest unoccupied molecular orbital. At that stage, though, there's no longer a vibrational mechanism, and therefore, because of the large energy gap between the ground state and the excited state, the only mechanism that's available to a rigid molecule, a fluorophore like rhodamin B, is the emission of a photon, and this fluorescence process typically happens on the nanosecond time regime, or 10 to the minus 9 seconds. Now, in some cases, we can end up having another radiative recombination process, which is known as phosphorescence. And phosphorescence is going to occur when we have a change in the spin multiplicity, which we've discussed previously. And we can consider that we have some ground state and excited state singlet. And we've got a photoexcitation process. And then we have intersystem crossing to a excited state triplet. And now in this process, we are going to have a spin flip during this intersystem crossing. And because of that, we are going to have extended lifetimes for that particular electron. So it's, imagine we'll illustrate it as spin up when it's in the triplet. It's going to be spin down. And prior to any kind of radiative recombination, we're going to have to wait for that spin flip to occur, because ultimately, once it goes back down to the ground state, it will have to have the same quantum numbers and profile as it did originally. Now, because of that spin flip, the phosphorescence time scale is extended, and typically we'll see phosphorescence on a time scale of 10 to the minus 6 seconds, all the way to 10 to the 0, raised to the 0 power, so that is microseconds, all the way to seconds. And typically this happens in systems that have large spin orbit